I previously alluded to the idea that we needed a way to measure the H3O plus concentration, or to get a general idea of it. And we have a way to measure that through an entity called pH. pH is a measure of acidity. The acidity or basicity of a solution is often expressed as pH, and pH is defined as the negative log of the H3O plus concentration. So the pH of pure water, now this is not the water that you're going to find in your puddle, this would be pure water, is negative log of 10 to minus 7, 1 times 10 to minus 7, and that is 7. So a neutral solution has a pH of 7. So you need to know the H3O plus concentration to find the pH, because you have to plug it in. If a pH is less than 7, the solution is acidic. If it's greater than 7, the solution is basic, and if it's 7, it's neutral. We can get the hydronium ion concentration back out by 10 to the negative pH. The hydronium ion concentration is 10 to the negative pH, and this is just from our log identities. From Kw, we can calculate the hydronium ion concentration if we know the hydroxide ion concentration, because those entities are equal to 10 to minus 14, or vice versa. So here we have some generic idea of acidity. So stomach acid is 1 to 3, limes are around 2, lemons are around 2. So you see here that most foods are going to be somewhat acidic. Milk of magnesia has a higher pH because it's supposed to neutralize acid. Ammonia has a high pH as well, and for example a 4% sodium hydroxide solution has a pH of 14. We also have an entity called pOH that we can use to express acidity or basicity. Generally, if we use this entity, we're generally talking about bases. So pOH is the negative log of the hydroxide ion concentration, and we can get the hydroxide ion concentration back out from our pH as 10 to the negative pOH. So the pOH for pure water is negative log of 10 to minus 7, so that is also 7. So you need to know the hydroxide ion concentration to find the pOH. If the pOH is less than 7, it's basic. If it's greater than 7, it's acidic, and if it's equal to 7, it's neutral. Also, keep in mind that the pH plus the pOH is equal to 14, because the hydronium and hydroxide ion concentration together is 1 times 10 to minus 14, and we use this scale as an indicator of pH and pOH. Notice that these are complementary to each other, so the lower the pH, the higher the pOH, and vice versa. A pH of 0 corresponds to a pOH of 14. pH of 7 is a pOH of 7. They're both neutral, and a pH of 14 corresponds to a pOH of 0. Here we review those identities. The pH plus the pOH is equal to 14 at 25 degrees C. You should definitely keep that in mind. It will help you work some problems. And also the hydronium and hydroxide ion concentration multiplied together, the products of those two things, is equal to the Kw, which is equal to 1 times 10 to minus 14. Alright, the negative log of the hydronium and hydroxide ion concentration is equal to the negative log of 1 times 10 to minus 14. Okay, so according to log identities, we can add those both together and get 14, and that's why the pH plus the pOH is equal to 14. So you should keep that in mind. If we're not talking about the pH of a solution, so if we're talking about an acid outside a solution, and we just want to compare relative strengths of acids and bases, we use an entity called the pK. So the relative strength of an acid or base can be expressed as the pKa for acids and the pKb for bases. The pKa is the negative log of the Ka, and we can get the Ka back out also as 10 to the negative pKa. The pKb is the negative log of the Kb, and we can get the Kb back out as 10 to the negative pKb. The stronger the acid, the smaller the pKa, okay, because pKa is the negative log. And the stronger the base, the smaller the pKb, because larger KB is equal to smaller PKB. Okay, so we're going to work some problems with that. Here's a conceptual connection problem. As the pH of a solution increases, what happens to the acidity of that solution? It increases, decreases, or remains constant. The acidity decreases.